Hi, welcome to 11th session on group theory. This session and the next session will deal with cyclic groups, the order of an element in a group. Both these topics are somewhat very closely interrelated, so I decided to keep them together. And before we start this, there is some remark which I have to make about yesterday's session, the last session, where we looked at two integers a and b. Then we looked at the smallest subgroup which contains a and b, namely az plus bz. We found it, and we found it is nothing other than d times z, where d is the least common multiple of a and b. Up to that I stopped, but there is something more I would like to say about it. Let's start with that. Okay, so let us look at a, b, or let us say non-negative integers, in fact positive integers, right? And then let's look az plus bz, which is same as, of course, z times a plus z times b. Okay, we saw this group is nothing other than d times z, where d all multiples of d, where d is the LCM, sorry, GCD of a and b. Okay, right. Now in particular, d belongs to dz, that is equal to az plus bz. Therefore, what we have is there exists integers u and v, so that d is au plus bb, right? So this, therefore, if d is the greatest common divisor of two integers, then I can always find integers u and v, so that d can be written as au plus bb, that is integral linear combination of a and b. This is known as Bezo's identity. Okay, those who have gone through my lectures on E and T, elementary number theory, will know this. Okay, already known for those who have seen this, right? Another important thing, therefore, suppose the GCD of A and B equal to 1, then I say A and B are relatively prime. Then in that case, if A and B are relatively prime, that is if A and B are relatively prime, or same as saying GCD of A and B equal to 1, implies there exists integers u and b and z, so that I can always write 1 as au plus b. That follows as a special case of this. Yeah. So if you have gone through E and T, you already know this, exactly the same proof, except there I never use the word subgroup, etc. Okay, this is a very important thing. You will see we will repeatedly use whenever we use group theory, in particular cyclic groups, order of an element, etc., etc. Okay, so this is one of the things which, okay, students don't learn properly, so they find group theory a little difficult. Okay, let's get on with it. So we will stop it. We will go to the topic of today's session. So cyclic groups. Okay, suppose G is a group. Maybe I should increase the pen. Let me J rectangle pen options. Yeah, it's thick. I don't know why it's slow. Okay, let G be a group. Okay, suppose the G is cyclic. Okay, if it's a cyclic group, if one is a cyclic group, if there exists an element A in G, so that the smallest subgroup generated by A, recall this is nothing other than a to the power n varies over all of Z. This subgroup is all of G. Is that definition clear? Yeah. Okay. Right. So let us do that. So let us look at examples of cyclic groups or non-cyclic groups also. The first important example is the additive group of integers, right? So that, for example, if I take 1, take a equal to 1, then in the additive notation, a power n is nothing other than a plus a n times if n is natural number and equal to minus a plus minus a if n is negative. This is minus n times, right? We had already seen it. Okay, that's how we interpreted. Do you remember? A to the power minus n, if n is positive, how did you define? We define it as the nth power of a inverse. And in the additive notation, a inverse is minus a. Is that clear? Okay. Therefore, what is the additive group of a? This is, that is 1 here, is 1, 1 plus 1, etc. And minus 1 plus minus 1, and so on. That means all 0, 1, 2, and minus 1, minus 2, etc. Therefore, it's all of z. Okay, is that clear? And notice that the let's go back to the definition. If G is cyclic, okay, that means there is an A in G such that G equal to cyclic subgroup generated by A. This A is called a generator. The group G. Okay. And this generator need not be unique. Okay, that's the next point I want to say. That is, there may exist more than one generator. For example, in the case of Z plus, okay, I can take A equal to 1. I can also take A equal to minus 1. Because what is the additive, what is the cyclic subgroup or the smallest subgroup which contains minus 1? It is n times minus 1, as n varies over all integers, right? Therefore, both plus 1 and minus 1 are generators. So, Z plus. Okay. So, pause, review, and proceed. Now, let's look at a second example. Let us look at Zn. This is the addition modulo n. Okay. And recall what are the elements? The elements are actually equivalent classes. What is the equivalent class? Of any k, let us say R, is if an integer m, a in z is divided by n, then I have a equal to q1 plus r, where r is 0 less than or equal to r less than n, right? This is by division algorithm. Okay, the equivalent classes are this. We will usually denote by only r. This is the set of all integers a, so that a belong to this if only if r is the remainder when divided by n. Okay, I hope all of you have mastered this now. Therefore, I will simply write Zn, okay, as only instead of 0, 1, 2, n minus 1. Is that okay? Instead of writing 0, 1, etc., or some books write like this 1, 2, and some other books are extremely careful, they write this. That is equivalence class of 1 modulo n. Okay, is that clear? Right. Now, 1 in Zn is a generator. Why? Because we will look at, okay, the equivalent, the smallest subgroup containing 1 is 1, 2, and that is 1 plus 1 n minus 1 times n minus 1 times, that is equal to n minus 1. After that, 1 plus 1 plus n time, that is 0. Right? Therefore, I get all of Zn. Right? Therefore, for each n, in n, this additive group is cyclic. Okay? Now, you see that there are two classes of cyclic groups which you have found so far the example. One is additive group of integers, the other one is integers modulo n, Zn, right? Very surprising thing which you will see later is essentially the only cyclic groups are these. You understand this? Essentially, what does it mean? Okay, slowly we will get to understand that. Okay, so it's like any cyclic group is Zn may come with a disguise. Okay, it may change its dress, okay, makeup, and come in a different fashion. Okay, we had already seen examples. We will come back to it. Right, let us look at a specific example here. Okay, take n equal to 8 for example. Let us look at Zn with addition Z8. Okay, so we already know 1 is a generator. Is 2 a generator? So what is the subgroup generated by this? 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8, which is 0. Okay, there are only 4 elements. Right? So this is not a generator. How about 3? 3 is 3, 6, 9, which is 1, and 9 plus 3 is 12, or 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10, that is equal to 2, and 2 plus 3 is 5, and 5 plus 3 is 8, which is 0. That means this is all of Z8. Therefore, 3 is a generator. Since 3 is a generator, its additive inverse in Z8 must be a generator. What is that? What is the inverse of additive inverse of 3? It is 5. Right? So let us look at 5. 5 is consists of 5. 5 plus 5 is 10, which is 2. 2 plus 5 is 7. 7 plus 5 is 12. 12, that is 4. 4 plus 5 is 9. 9 is 1. Okay. And 1 plus 5 is 6. And 6 plus 5 is 11, which is 3. And 3 plus 5 is 8, which is 0. So this is also Z8. So 5 is also a generator. Is that okay? Right. Now notice that we had already observed with 1 belongs to this subgroup 5. That means the cyclic group generated by 1, the smallest subgroup containing 1 is contained in this. But this we already know is Z8. Therefore, the moment I found 1, I need not have carried out these operations. How many of you understand this? Okay. PRP. Okay. So I drew some pictures. We will come to it a little later. Okay. Yeah. So is that clear? The logic? Now I want you to do something more. Okay. For example, what is 4? We are done. 2, 3, 5 and 4, 6, 7 remain. Right? Will you do it? Okay. I will quickly do without spending time. The cyclic subgroup generated by 4 is 4 and 8, which is 0. Cyclic subgroup generated by 6 is equal to 6. 6 plus 6 is 12. 4 plus 6 is 10, which is 2. 2 plus 6 is 8, which is 0. Right? And 7, remember 7 is additive inverse of minus 1. Right? Yeah, 1 plus 7 is 0, 8 and hence 0. Therefore, it is the negative of 1. Since 1 is the generator, 7 is also a generator. How many of you understand this logic? Right? So, these are the things. Keep this example, we will revisit them. Okay. Now, let's look at an example 3 now. Let me change the color now perhaps. Example 3. Fix a natural number n. Okay. Remember un, nth roots of unity. All nth roots of unity, which is n in number, which is xi to the power k, 0 less than or equal to k, usually denoted by omega. Omega to the power k, this is omega. If you want to read does w, that's fine. And 0 less than or equal to k, strictly less than n, and omega is exponential 2 to the power minus n. We had already seen it. Okay, this is also cyclic group. Because omega itself by very construction is cyclic group, right? Omega is a generator. Okay, understand this? Here. So luckily we seem to have seen all cyclic groups. Let us see whether we can get something else. So let me change the color now. So let us do example 5. This looks a little fluorescent. If I do not know you like this, so let me change the color. So example 5. Let us look at units in Z8. Remember, Z8 has two operations. Under addition, another is multiplication. Under multiplication, one is a multiplicative identity. Not all elements are invertible in Z8. And what are the elements? If so, what is Z8? As remember, Z8 is Z8 is 0, 1 up to 7, right? And we know an R in Z8 lies in, that is the units of Z8, that is it's invertible under multiplication. If and only if GCD of R and 8 is 1. That is R and 8 are relatively prime. Right? So, what are the elements of units in Z8 under multiplication? They are, of course, 1 and 2 is not, 3 is there, 4 is not, 5 is there, 6 is not, 7 is there, and that's it. Right? Now let us see what is the multiplication. What is 1 a generator? This consists of only one element. Let us look at 3. Is 3 a generator? 3 is 3. Next is, remember, under multiplication, therefore it's not 2 times 3, it is 3 squared, which is 9, which is equal to 1. Right? That's it. Therefore it consists of only 1 and 3, because if I multiply by this, I will get back to 3. Therefore 3 is not. Let's look at 5. Okay, 5 is what? 5 and 5 squared, which is 25. 25 is also 1 mod 8. Therefore it's 1. Therefore it's also again 1 and 5. Maybe perhaps 7. 7 is 7. 7 squared is 49, which is equal to 1. Therefore, it's again 1 and 7. Oh, again I forgot. I forgot to share the screen. So let us look at U8. Okay. And Z8 has two operations, binary operation. One is addition, the other one is multiplication. And one is the multiplicative identity. UZ8 stands for all the units. That means those elements are said that R has a multiplicative inverse. When does R has a multiplicative inverse? If only if R and 8 are relatively prime. That is the greatest common divisor of R and 8 is 1. Okay. Therefore, what are the elements of UZ8? 1, 3, 5 and 7. Right? 2 is not, because 2 and 8 has common divisor 2. 4 is not, 4 and 8 has common divisor 4. 6 and 8 have common divisor 2. Therefore, these are the only elements. Right? Now, what I did was look at the smallest subgroup which contains this, that is all 3 to the power n. We found it has only 2 elements 1 and 3. 5, it has 2 elements 1 and 5. 7, it has 2 elements 1 and 7. Right? Now I have 4 elements in this group. Use the date has only 4 elements. What are they? 1, the multiplicative identity, 3, 5 and 7. Right? And it's abelian. Okay, right? Because multiplication Z8 is abelian, I mean commutative. Therefore, it's an abelian group of 4 elements. And other than identity, all elements, their square is identity. That is, 3 square is identity. Call 3 as A, B as, call 5 as B, B squared is identity. Call 7 as C, C squared is identity. Have you seen such a group? Yeah. In the last session, we have seen such a group. And we also found what we call as a Klein's group. And we there, something happened. What happens when I multiply any 2 of ABC? I got the third element. Right? Now I'm just curious. Does it happen here? Let us check. So let A equal to 3, B equal to 5, C equal to 7. Right? Therefore, what is A times B? That is 15. 15 is modulo 8, it is 7. Therefore, it's C. And what is 8 times C? That is 3 times 7, 21. That is 5. Right? 2 times 8 is 16. 16 plus 5. Therefore, it's 5. That is B. And what is B times C? That is 5 times 7, 35. That is 4 times 8 plus 3. Therefore, it's 3, which is A. So, you see that the units, this group, okay, looks almost similar. Looks like the Klein 4 group 4. Okay, which we again we saw it is Z2 cross Z2. Right? We also saw something else. Another group which has G, which consists of only these elements: identity permutation, the transposition 1 2, the transposition 3 4, and the cycle decomposition 1 2 3 4. This also, if I call A B C, A squared equal to B squared equal to C squared equal to the identity element, identity permutation. Okay, and product identity two elements are the same. That means all these groups G, U of Z8 and Klein's 4 group all look similar. Right? So you can see there are 4 elements. If I abstractly denote the elements by identity A, B, C, I cannot distinguish them. A squared equal to B squared equal to C squared equal to identity, and product identity two elements is the third element. Yeah? Something interesting is happening. Okay, what is it? Let us wait and see. Okay. The last example we will do again. Okay. Therefore, what is the conclusion? U of z 8 is not cyclic. You should not forget that was our original aim. Okay, it's not cyclic. Let me see whether I share the screen. Yes. Okay, at least we found one group which is not cyclic. But there are many groups which are not cyclic, because remember, if G is cyclic, that means, okay, there exists A, so that this is equal to G. That means any element, if you take X and Y in Z, then X is something like A to the power M and Y is something like A to the power N, where M and N are integers. Therefore, what is XY? That is A to the power M into A to the power N, which is A to the power M plus N. What is YX? That is A to the power N into A to the power M, which is A to the power N plus M, but these two are equal, right? M plus N is same as N plus M, therefore they are equal. That means for all XY in G, I have XY equal to YG. Sorry, YX. That is, any cyclic group is abelian. Therefore, to find a group which is not cyclic, I just have to produce a non-abelian group. Therefore, for example, S3 is non-abelian. And that means S3 is not cyclic. Okay. So let's go back to this example. Why this is interesting? U of Z8. Why is it interesting? This example is interesting. Why? It says this is an abelian group, but not cyclic. Okay, do you understand? Pause, review, proceed. So, for that matter, same example, Klein 4 group and the other group G, which was 1, 2, 3, 4, 1, 2, 3, 4, and identity. This group also abelian but not cyclic. Okay. Now let's go to the next example. I think this example must be 6. Let us look at example 6. Okay. Now let's look at Z7. Right. Now what is you remember 7 is a prime. Therefore, if I take anything 1 less than or equal to or less than 6, less than or equal to 6, okay, then R belongs to this, because it's relatively prime to 7. Therefore, U of Z7 has all these elements 1, 2, 3, 4, 5, and 6. Is that clear? Okay. Now let us see whether this is cyclic. Is Z7 cyclic? That's a question. Of course, one is ruled out because this will be singleton 1. Therefore, this is not a generator. Let us look at 2. 2, what are the generators? Remember, it's a multiplication of 2, and 2 times 2 is 4, and 4 times 2 is 8, which is 1, and 1 times 2 is 2. Therefore, I repeat. Do you understand this? Yeah. Therefore, 2 squared. So it should have 2, 2 squared, and 2 cubed. But 2 cubed is already multiplied identity. Therefore, 2 power 4 will be 2. You understand this? And what is its inverse? Remember, 2 times 4 is 8, which is 1. Therefore, the inverse of 2 is 4. Therefore, right? Therefore, 4 is also not a generator, because both generate the same subgroup. Therefore, 2 and 4 are not generators. So, please understand, PRP. Let us look at 3 now. 3 is 3 and 3 squared is 9, that is 2, and then 3 cubed is 2 times 3, which is 6, and 6 times 3 is 18, 18 is 4 modulo 7, and 4 times 3 is 12, that is 5, right? And 5 times 3 is 15, that is 1. 15 is 2 times 7 plus 1, right? So I have 1 element, 2 element, 3 element, 4 element, 5 element, 6 elements. All 6 elements I got, right? Therefore, this is nothing other than Z7. Okay, make sure you understand. And do you understand this? Instead of 27, what I did was I multiplied 2 times 3. If I do 27, then 27, then by 7, okay, 3 times 7 is 21, 6 remainder, therefore I have to write it. You don't know how to do that, you can always use simplify your luck. So simplify your logic computation. Is that okay? If you are struggling, please pause, review, proceed. Now what is the inverse of 3? So what is that I have to do? 3 times something, okay, I have to be 1, right? You already found it, because what did you do? 3 times 5 we found is to be 3 times 5 is 15. That is 1. You understand? Therefore 3 times 5 is 5. Yeah. Therefore what do we have? So this is 5, and which is all elements in Z7. Therefore 3, 5 are generators. Whereas 2 is not a generator, 4 is not a generator. So what are the things we left out? So 1 is ruled out, 2, 4 ruled out, 3, 4 we are done, 3 and 5. Okay. The only remaining thing is 6. Let us look at 6 now. 6 is 6 is square 6. 6 squared is 36 divided by 7, that is already 1, right? 6 squared is 36, that is 5 times 7 plus 1, that puts 1, that puts answer only 2 elements. Yeah. So what have we shown? We have shown that U Z7 is cyclic and 3 and 5 are generators. Okay. So pause, review, proceed. Okay, about half the time is over. Is this clear? Please review this. So we are looked at, we have defined what is meant by cyclic group, and we defined what is meant by generator, and we also saw generators need not be unique, and we also saw examples of cyclic groups and also non-cyclic groups. And whenever there is a cyclic group, in the finite case, we try to find all the generators. Yeah, it's a very good exercise, and my suggestion would be to make sure you deal with something like Z12, okay, Z6 or something. Yeah, Z6, Z12 you do with respect to addition, and also you try to do with respect to the multiplication, right? U of Z6, U of Z12, try to do. Once you are done, you will see that you will be very, very confident about all these things, right? Okay. Now we are going to the next topic. What is the next topic? Order of an element. We will do that. So next thing is right. So let G be a group. A is some element. The first thing I say A is of finite order if there exists a natural number n so that A to the power n is identity. Otherwise, A is of infinite order. What does that mean? For every natural number n, A to the power n is different from identity. Remember natural number. Natural numbers for me starts from 1, 2, 3. Starts from 1. Is that okay? Right. So, let's look at. So, what you are saying is that if in Zn, each element A, okay, is of finite order. Right? For example, okay, we are seeing that simplest thing is A times n, which is n times A, which is 0. Because it's divisible by n. Right? Therefore, it's 0 in Zn. Okay? Right. More generally, okay, if G is a finite group and every element and A is in G, then A is of finite order. Why? Because look at, let the number of elements in G be equal to n. Then I claim A to the power n is identity. Okay? We have to prove that. Okay? Let us assume, I hope I can prove it. So I have A. So let us look at this as n. Okay, A to the power m. The m is over z. Okay, let's not do this. I will simply say A is of finite order. That's good enough for me. Okay. I don't want to say A to the power n is identity. Okay. It's actually true, but I don't think I'm in a position to prove it now. Okay. So let me only prove for some m, A to the power, natural number m, A to the power m is identity. Okay. That's all I want to prove. The proof you had already seen because since this is a subset of z, that means there exists integers r and s in z, r not equal to s, let us say r less than s, so that A to the power r equal to A to the power s. This means A to the power s minus r is identity. Remember, s minus r is a natural number now. Okay, that's it. Yeah, is that definition clear? Whereas in the case of z under addition, okay, start with any non-zero element a not equal to 0 a in z, then n times a is not different from 0 for every natural number n. Right? Okay. Therefore, each non-zero element is of infinite order. Okay. So notice that so far I have not done what is meant by an order of an element. I only said give me any element in a group, either it's of finite order or it's of infinite order, mutually exclusive cases. I do not know how many of you have gone through my linear algebra book. See, I will say a vector space is finite dimensional before even defining what is meant by dimension. Right? If there is a finite subset of the vector space V, the smallest subspace containing that finite set is V, then V is finite dimensional. That's my definition. I don't even know the definition of a dimension at that time. Similarly here, I am not defining the order of an element first. I am simply saying it's a finite order. Do you understand the subtlety? Yeah? Okay. Let's go back further. So now we are ready for the definition. Let A in G be of finite order. Then the order, let us say Y of M, is the smallest positive integer n such that a to the power n is identity. Let's try to understand this better. What this means? Suppose A is a finite order. Let's look at the set of k natural numbers so that a to the power k is identity. This set is non-empty. This is a subset of natural numbers and is non-empty. Because A is a finite order, there exists at least one k natural numbers such that a to the power k is identity, right? Therefore, by well ordering principle, there exists the least positive integer ya, okay, in this set. That OA is less than or equal to K for each K in this set. If you want to call this set as OA in S or ECS in S. Do you understand? So that least positive integer was we denote by Y of A, read it as order of A. Okay, is that clear? And if A is of infinite order, we let this is a notation equal to infinity. This is just a notation, a convention or notation. Is that okay? Right. So when you go back, you can see in the group of this, for example, in this group, okay, take 2, you see that the order of 2 is 3. Okay, this is a multiplicative group. What is order of 3 here? Is 3 because 2 squared, 2 cubed, 2 cubed, 2 cubed is 1. Right? Similarly, order of 4 is also 3. Why? 4, 4, 4 squared is 16. 16 is we are modulo 7, right? Is 2 and 2 into 4 is 8, which is 1. This is 4 cubed. 4 cubed is 64 if you want. Okay. So 9 times 7 is 63 plus therefore 1. Is it okay? Whereas order of 3 is 6. So similarly you can do with similarly in Z8 also we have seen not all elements Z8 is cyclic but not all elements have the same order because if I take with 2, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, which is 0. That means order of 2 is 4 in Z8. Yeah? Please go through those examples. Make sure that you understand. Now, before we stop, I would like to formulate a theorem, okay, about elements of finite order so that we can freely use all these observations later. There are actually observations, but I would like to call them as a theorem. Oh, this seems to be the last page. I'm about to put a few more pages. Oh, there is something which allows me to write. I had forgotten the previous journal, new page after. Okay, now let's do that. So this is a theorem. Let A in G be of finite order. Say order of A equal to n. Then what are the following result? the first thing is I want to say order of, okay, if suppose a to the power m is identity, implies n divides m. That is, m must be a multiple of n. And 2, for some integers r and s and z, a to the power r equal to a to the power s, that should imply r is congruent to s modulo n, which is another way of saying n divides r minus s. And third, all the elements a, identity a squared, a to the power n minus 1, they are all distinct elements. I should not write a set theoretic notation, simply say this, that is e, a squared, a to the power n minus 1 are all distinct. That means this is this, okay. Is that definition clear? Okay, let us look at this. Proofs are easy. Now suppose m is an integer such that a to the power m is identity, right? So I want to prove n divides m. What do you think I should be able to use? By now you should know how many times I have to use. What are the most important result in elementary number theory? It is division algorithm, right? So whenever you want to say something is multiple of something, you want to find the remainder, okay, you have to use this. And whenever you want to use GCD, you have to use Bezoar's identity. Keep that in mind. This will save a lot of your problem. You don't have to remember. You remember the principle. You don't remember each and every proof now. Okay. Two results are important. One is division algorithm. Whenever I want to say something is a multiple, I want to find the remainder. Second thing is, with respect to congruence relation also, I have to do remainder. Addition model or multiplication model or what is that I have to use? Division algorithm. But when it comes to using something to do with GCD, most often or relatively prime, I have to use Bezoar's identity. Please remember these two golden principles. Okay, let's go back. So let us write. Therefore, m by divisional algorithm, it will be qn plus r, where 0 less than r less than n, right? Now I know a to the power m is identity, but a to the power n is a to the power qn plus r. By law of exponents, a to the power qn plus a to the power r. By again law of exponents, a to the power n times q times a to the power r. But a to the power n is identity, therefore e to the power q, a to the power r, therefore a to the power r, right? Therefore what I have found is a to the power r is identity, right? Now notice this, r cannot be positive. If r is not equal to 0, then it is a natural number which is strictly less than n, but a to the power r is identity. This contradicts our choice, right? If r is not equal to 0, then r is a natural number less than n, and but a to the power r is identity. This contradicts our assumption on our definition of order of a, which is n, right? Therefore r has to be 0, that is a m is q times n, that means n divides m. Okay, so one is proved. Now 2 is obvious. Suppose r and s are integers and a to the power r equal to a to the power s, right? Then what do? I multiply both sides by the inverse of a to the power s. A to the power r into a to the power s inverse, and a to the power s into a to the power s inverse. But a to the power s inverse by definition, okay, this is going to be a to the power r minus s, because a to the power s inverse we had already seen is a to the power minus s, and law of indices says a to the power r is equal to identity. Okay, that means n should divide r minus s. Okay, this is a, and using congruence relation, it is same as saying r is congruent to s mod n. Okay, is that clear? Yeah, right. Okay, now what is the third? Third is, suppose 0 less than or equal to r, less than s, less than n, right? Suppose a to the power equal to a to the power s. All elements here, we want to say they are all distinct. All these elements are distinct. Suppose it is not. Okay. Again, with the loss of generality, let me assume, okay, uh, r is less than s. Therefore, this means a to the power s into a to the power minus r is a to the power r into a to the power minus r equal to identity. That means a to the power s minus r is identity. Correct? But remember, s is here, therefore s is, and s minus r is less than s. Okay, r is greater than, is again greater than or equal to 0. I am reducing. But this s is strictly less than n. Therefore, again I have a contradiction. Okay. Yeah, if s minus r is not equal to 0, suppose it is not equal to 0, then it is not, it's a positive. Therefore, I have a natural number which is strictly less than n, but yet to the power that natural number is identity. That's a contradiction. Therefore, r has to be s. Right? That means all these n elements are distinct. Right? Now, as an immediate corollary, you see that what is this? This is just a to the power 0, a to the power 1, a to the power minus n1, etc. Because this is a to the power k, k varying over integers. So if I start with k equal to 0, I have identity a to the power n minus 1, and when I write a to the power n, which is identity, and a to the power n plus 1, which is a to the power n times a, which is a, and so on, right? So it keeps repeating. Therefore, the cyclic subgroup generated by a is precisely this. Therefore, order of a is nothing other than number of elements in this. Okay. So we have about 52 minutes. So I have another, let's say, 5 to 7 minutes, right? Now I want to give one more important example. I forgot when we come. Okay. So I want to compute the order of one particular element. We had already done in Zn and u of Z8 and Z7, etc. We have done that. Okay. Now I want to do a non-trivial example. Okay. With that, I will stop. Okay. Now let's look at Sn. Let's assume n is greater than or equal to 3, right? And look at a cycle I1, I2, In. So let me assume this is n, some n greater than or equal to 3, capital N. So because I had it, you understand? Now this sigma is an element of capital N, and I want to know what is its order. Is the question clear? If you remember right, we had already seen when we did a permutation group, symmetry group, we have shown that sigma power n is identity. Right? We had worked out examples. We always saw whenever there is a cycle 1, 2, 3, then its cubed is identity. Okay, identity, this identity I write as E, and so on. We have done, but it's a very general thing. Okay, what are the thing? 1 less than or equal to I1, I, n. Okay, these are the elements which are less than or equal to n. I don't. Okay, so I don't want to waste the pictures which I had drawn beforehand, because when I try to draw here now, it will take a lot more time. So I drew it earlier. So I remembered that. I will finish with that example. Okay, let's go back. Let's go to the essentially the first page. Oh, okay, it's not first page, it's the 8th page, right? Now let us look at, these are the position 1, 2, 3, the position n. In position 1, I1 is there. In position 2, I2 is there. In position 3, I3 is there. Position n, In is there, right? Now when I apply sigma, what happens? I1 goes to I2. That means I1 goes to position 2 and I2 goes to I3. That means it goes to position 3 and so on. Do you follow that? And what happens to here? This IN comes to position 1. Right? Right? That's a cycle, right? Now suppose I apply sigma once more. This means totally I had applied sigma squared from this configuration to this configuration. So what will I have? This will become IN minus 1 will come here. IN will go here and I1 will go here. That is position 3. It will come. If you want me to use the earlier notation, yeah, this is 3. Right? Here it comes. You follow that? Okay. And once more, if I apply this is sigma cubed, this sigma squared, apply sigma, then IN minus 1 will come here, IN will come here, and so on. Is the picture clear? So you can see, if I take any ij, apply sigma r, okay, it will move to ij plus r. For example, r equal to 1, what happened to I2? It become 2 plus 1. Okay, if I will take n, okay, j equal to n, okay, then it will be, and r equal to 2, what will be? N plus 2. Where will it be n plus 2? Now it says, are you following? It's I, j plus r. You are removing r times. But then remove j plus r may shoot out greater than or equal to n. Right? Greater than n. In that case, what is the meaning? If it is greater than n, you read it modulo n. That means, for example, suppose my n is 10, r is 7, j is 6. Then what will happen to j? If I apply 7 times, it is going to be 13. I13. What is I13? Because it's only 10, it will be I3. Have you understood? So, this clearly shows, how do I go to the last element? Okay, last page. Okay. Therefore, what you have shown is sigma k is not equal to identity if k is less than n, strictly, okay, 1. Okay, and sigma n equal to identity. Therefore, okay, order of the cycle is n, but that is nothing other than the length of the cycle. I think I should have screen shared. Yes, I did. Have you understood that? Okay, please go through, discuss with your friends this last subtle point. Okay, what you have shown, if I have a cycle of length k in Sn, then this order is k, because I1 goes to I2, second time I1 goes to I3, third time I1 goes to I4, and so on. Okay, k minus 1 step, I1 would have gone to Ik. When I apply once more, Ik would have gone to I1, right? Therefore, okay, the order of a cycle of length k is the length, namely k. Okay, so this will allow us to compute the order of any element in a symmetry group. Okay, in fact, we are just, I could have done it if there is time, another 5 minutes, but just understand. Okay, we will do it in the next session. Okay, I hope all of you enjoyed. Take care. As usual, revise. The important way to master anything is to learn it thoroughly, and after that, close the book or anything, video, don't watch it, and try to recall, revise. If you get stuck, open the book or go to the video and again watch. Okay, this way you will master. And this way of mastering will become faster if you practice it very sincerely for about 10 to 15 times. Believe me, it really happens. Okay, take care. We'll meet again.